In section 3.4, we're going to be talking about linear programming. Some real-world problems involve multiple linear relationships. Linear programming accounts for all of these linear relationships and gives solutions to that problem. So basically what we're going to take a look at today are types of situations where there's multiple constraints to a given situation. I guess in a way more vague sense, I would relate this to when you're trying to make plans and you feel like there's a million different things kind of affecting how you're going to make that plan, and your goal is to think of the best possible scenario to have everything run smoothly. Here we're going to look at an example of you running the school spirit shop, of there being different constraints on your budget and trying to maximize profit. So we're going to represent those constraints to the situation as a system of linear inequalities. And from there, when we graph all of those inequalities and we shade where everything overlaps in that graph, we call the feasible region. And then the quantity that we're trying to either maximize or minimize, usually it's something related to cost or profit, is going to be modeled by an objective function. And this is going to make a lot more sense in our real-world solution, or in our real-world example. The last thing that I want to talk about before we get started here is the vertex principle of linear programming. If there is a max or a min value of a linear objective function, it's going to occur at one or more of the vertices of that feasible region. So when we graph that and we have that kind of polygon figure, wherever the vertices are on that polygon is where the max or min is going to occur. So let's look at two examples. One is just going to be dealing with numbers. The next one is going to be an actual real-world example. What is the point in the feasible region that maximizes p for the objective function p equals 2x plus y? And then here we're going to have a list of our constraints, or our linear inequalities. We're going to graph all of these individually and then see the overlapping region, find our vertices, and go from there. So here I have four inequalities as my constraints. And when I graph them, again, same as usual, I need to get these into slope-intercept form to be able to graph. So in my first equation, I'm going to manipulate it to get it to slope-intercept form. My y-intercept's at 2.5. I go down 1 over 2, and I'm going to graph or shade below that region because it's less than or equal to. In my next inequality, I move the x over. I multiply by -1, which then flips that inequality. And then I start at -2, go up 1 over 1, and I shade above that region. So now I kind of see an area where both of those overlap. When I graph my other constraints, it's going to make this overlapping region a little bit smaller. X is greater than or equal to 0 is really just my y-axis. It's a vertical line going through x equals 0. And I want to shade above that region, so I go to the right. And then finally, y is greater than 0 is the x-axis. I have that shaded, and I want to go above that. So I see that my feasible region is this kind of quadrilateral in the middle here. And my vertices are where either the max or min is going to occur. And then what I'm going to do is I'm going to take these vertices and use those x, y values, plug them into my objective function. Whatever gives me the highest value will maximize that function. So I want to evaluate p at each vertex. So again, here's my objective function, and my vertices are listed here. What I'm going to do is plug each vertice into my equation and see what maximizes it. So here when I do 0, 2.5, I get 2.5. For the next one, I get 7. The next one, I get 4. And finally, at 0, 0, I get 0. So I see at that coordinate 3, 1, I get 7, which is my maximum value here. So in conclusion, what I'm going to say is that p has a maximum value of 7 when x equals 3 and y equals 1. So let's take a look at this in a real-world example. Let's say you are screen printing t-shirts and hoodies to sell at the South High Spirit Shop, and you're working with the following constraints. You have at most 20 hours to make clothes. You don't want to spend any more than $600 on supplies, so that's your budget. And you want to sell at least 50 items in your store. So given all of those constraints, how many t-shirts and hoodies should you make to maximize your profit, and what would that maximum profit be? And before we get started, here's some other important information to get started here. For our t-shirts and hoodies, it takes 10 minutes to make a t-shirt. It costs $4 in supplies to make a t-shirt, and your profit here would be $6 per shirt. On the other hand, for hoodies, those take 30 minutes to make. They cost $20 to make, and we can make a potential $20 in profit from that. And as we get started here, Let's define our variables. Let's let X equal my t-shirts and Y equal my hoodies. And then my profit equation is going to be 6 times however many t-shirts I sell plus 20 times however many hoodies I sell. So let's represent all of that information as certain constraints. So $10 to make, or 10 minutes to make a t-shirt plus 30 minutes to make a hoodie, I want to be less than or equal to 20 hours of work or 1,200 minutes. My next constraint, I want to make at least 50 items of clothing, so X t-shirts plus Y hoodies should be greater than or equal to 50. I want to not spend more than $600, so this is going to represent my budget. $4 to make a t-shirt plus $20 to make each hoodie should be less than or equal to $600 in total. And then finally, since again I'm working in a real-world situation, anything dealing with a negative value isn't going to make logical sense, so that's why I'm going to have my constraint of X is greater than or equal to 0 and Y is greater than or equal to 0. Essentially what that means is I'm at least going to have 0 hoodies and 0 t-shirts. I'm not going to have negative hoodies or t-shirts. That just wouldn't make sense. Having those two constraints basically just limits us into the first quadrant. So if I graph in the first quadrant, I don't even necessarily need to graph these inequalities as well. Now I'm going to have my X and Y axis. On a test or anything, I'll have it kind of labeled out for you. Here our graph is going to be a little bit different. It's not going to be 1-to-1 per block, just because I want to have it to zoom in and be able to fit, and we're working with larger numbers. So t-shirts is X, hoodies is Y. I'm going to have my X-axis go up by 10s and my Y-axis go up by 2s. And then I'm going to graph each inequality. Again, as I do these, I need to get this into slope-intercept form. So my first one, I have Y is less than or equal to 40 minus 1 over 3X. Here, typically, since that 40 isn't shown on my Y-axis, I kind of plug in values like the 30, 60, 40 to then make my inequality from there, just in the middle of my graph. So this is what that first equation would look like, and I want to shade below. That next equation, I just got to move the X over to get it into slope-intercept form, and I graph that below. And then I graph that above because it's greater than or equal to. And my next inequality, I get that Y by itself. And then I start at 30, and my graph would look like that. And here I want to shade below. So I kind of see that middle, it almost looks like a trapezoid, is going to be my feasible region. And then again, X equals 0 is here represented, so I want to be to the right of that line. Y is greater than or equal to 0 above there. Again, that basically just limits me into the first quadrant, which is what I want. And here I can see my final kind of figure that I have is my feasible region over here. And my vertices are where either the maximum or minimum will occur. So I have the vertice 25, 25, 75, 15, 120, 0, and 50, 0. And what I'm going to do here is I'm going to plug this into my profit equation, and I'm going to see what maximizes that profit. So I'm going to plug in each vertice. If I sold 50 t-shirts and no hoodies, I would make $300. If I sold 25 of each, I would make $650, so that's a little bit better. If I sold 75 t-shirts and 15 hoodies, I would make $750. And finally, if I just sold 120 t-shirts, I would make $720. All of these combinations fit all of my constraints, but only one of them is going to maximize my profit. And here, I can clearly see that that's going to be if I sell 75 t-shirts and 15 hoodies. So in conclusion, I can maximize my profit by selling 75 t-shirts and 15 hoodies. That maximum profit would be $750.